I want what your opinion was about last week's class. And type your opinion. Let me see. I want to give you my opinion and then decide and tell you what I'm going to do today. But before that, I want to hear yours first. Yes, one person has commented. I'm looking for, okay, I've heard from Ugojuku has commented. Adesola, the network was poor. Good. One more. I just want one more comment before I give you my own comment. Just one more. Be quick. The rest of you, say something. If you were in class last week, what did you think about the class? About the lecture, about the time, that hour? Adesola said the network was poor. Okay, those of you for whom the network was not poor, what do you think? I want you to talk so that you won't be biased by what I'm going to say. I have my own comments, which I will give you now. One more comment and I will give you mine. So the rest of you take the challenge, just one person more to say, okay, had a little issue understanding because it was a bit dull. Good. Let me tell you, the last class was exceedingly dull. And I went home to think about, from my own side, what could be the cause. I don't know whether you will agree, but you can reserve your comment on my own until the end of the class. I think there are certain weaknesses in your background. There are certain things you have memorized that is not allowing you to move. And today, I've decided to go back. I'm going to give you that class lecture again. And I will now begin with some of the things I think are weak in your background. You've been passing your calculus, passing all these things, but you may not have taken some things beyond memorizing them. And you cannot advance that knowledge unless you unshackle yourself from memory and understand the principles behind them. So, because the lecture of last week is going to be extremely difficult for somebody who doesn't understand the logic of the basics. So, if you pay attention today, two things will happen. You will see that I am just repeating what you have been taught, but I am now emphasizing understanding it. And I would be slow and be ready to hear any questions you may have. Some of the things you think you know, that you actually might have even taught other people. I want to go to the depth of it because we need it now. Because now we are advancing the knowledge beyond what you knew before. And I will show you where we are at and where we are advancing it to. It doesn't matter to me if we do not cover beyond the scope of last week. But it is important that even if we study little, let that little be fully understood. So that's what I'm trying to do today. I'm going over, but I'm not just going over it. I've added some background work. And this background work is taking you to secondary school levels, almost as far back as that, where concepts of limit, continuity, and differentiability were discussed. And then once we understand that, it will be easy to expand that to the new area. But if you have difficulty in understanding that, then we are going to have problems, which I don't want us to have. So that is the reason why I wanted you to tell me what your opinions are. So we're going to start. You remember this is where we started last week. We said, I said the issues are not hard to understand, but they will be hard to understand for somebody who doesn't understand the logic of the basics. And they are fundamental to all tensor analysis. If we don't get this right, it is no point going beyond this space. We have to get this right, because if I go to what I had planned for today, if you don't understand what we did last week, it will just be adding insult upon injury. It will just be getting harder. So it is better for all of us that I go and revise that. So pay attention, ask questions. Do not hesitate. I will not get angry. If you ask questions that looks very simple, I will answer you. So be careful to note any area of difficulty. If you are specific, you will be assisted. And I say, how do you differentiate with respect to a large object? That is the issue. This is important because every definition of differentiation involves a division. Every time you define the differentiation, I will define it here again, and you will see that anytime you are defining differentiation, there is a division involved. But we are not allowed to divide with respect to a vector, and we cannot divide with respect to a tensor. Products are defined, but divisions are not defined. In vectors, in vectors, see the number of products that are defined. You have multiplication by scalar is defined, dot product is defined, cross product is defined, tensor product is defined. Now, when you get to tensors, so many products are defined, but no division is defined. So that is where the mathematics we will do now will differ fundamentally from the mathematics you knew before. Because the mathematics you were doing before, all your calculus was calculus of scalars. When you begin to do derivatives of vectors and tensors, there are new problems. And we will use special new ideas to solve that. When we bring those ideas in, it is only those who fully understand the previous idea that can cope. Those who do not understand the previous idea will not cope. So just bear that in mind, be patient, and if you are not, if I'm losing you, stop me and I will stop. Go to the chat room and ask your question. I will continually look at the chat room and I will see what questions you are asking, and I will concentrate on what is problematic to you, even if it means that we will not go beyond what we did last week. But if we can understand that, that is a lot of progress, because it was clear to me that the class was not coping last week. It was clear. I could feel it, and I have thought about it, and I want to solve that problem as much as I can. So that's what I'm going to do now. So it is the fact that whereas in scalar, multiplications and divisions are defined, but in tensors, only products are defined. No division is defined. So anytime anything has to do with division, we have to come up with new definitions for that thing, because there is no division whatsoever in vectors and tensors. Yet, derivatives can be taken. Derivatives can happen. Then how is it possible? And it is possible because we are going to introduce new concepts. These concepts are new to you. So, but I am telling you that you will understand the concept, provided you are not just cramming the previous work. If you were cramming before, I will bring it back to you in such a way that you will now try to understand it. Don't cram, just understand the principles, and then you can use the principles to understand these new concepts. So this is important because every definition of differentiation involves a division. And we are not allowed to divide with respect to a vector or a tensor. How then do we define differentiation with respect to a vector or a tensor? That is the question we are trying to answer today and next week. How do you differentiate when you cannot divide? Is it possible to still be able to differentiate when you cannot divide? And because of that, we are going to be introducing the idea of the Gateau differential as the solution to our inability to divide by tensors when we want to define a derivative. So the Gateau differential is a generalization of something we already know. So we will get there and we'll see the generalization, then we can move on from there. So let me now go to the next thing. Limits continuity for real scalar domains. Limits and continuity for real scalar domains. Here, I'm just telling you what you already know. I'm not bringing anything new. And if any sentence or any line here gives you problem, tell me and I will explain it again. So let's go. Today, right now, we are talking about what you already know. So let us say X naught and W naught are all real. You know that this symbol here, I mean they belong to the real set. That is, they are all real. We can say that the limit of a scalar valued real function, that is a scalar value function of a scalar argument. That is, the function itself is scalar, the argument is scalar. I will talk a little bit on that. Both the function and this argument are scalars. What do I mean by that? If you say y is equal to x squared, if x is equal to 2, that is the argument. If x is equal to 2, that's the argument, then y is equal to 4. you can see that in that case, the argument 2 is scalar, and the result of the function 4 is also scalar. So we say that y is equal to x squared is a scalar valued real function of a scalar argument. If we are to say it in full, because the input, which is the argument, is scalar, and when you evaluate the function, the result you get is scalar. We will get to situations where that is not true. But in this particular case, everything if I tell you differentiate that thing, you can differentiate it. If I tell you integrate it, you can integrate it. If I tell you to do anything with it, you can do, because all the calculus you have been learning up to this point was focused on real valued functions of scalar valued functions of scalar arguments. In that case, we say the limit of any function that is so defined as real x tends to real x naught is equal to real w naught. If we say that, we mean that if any pre-assigned real number epsilon, no matter how small, is if for any pre-assigned real number epsilon, which is positive, any real positive number, we can always find a real number delta such that the difference between f of x and w naught can be made smaller than epsilon. Remember, we are pre-assigning epsilon. That is, we are choosing it beforehand. That's what we mean by pre-assign. So let us say we start by saying let epsilon be 0.005. Let us say you say let epsilon be 0.005. We can find a situation whereby whenever we are inside that limit of delta, we can make sure that the difference between the thing on the left and the thing on the right will be smaller than that. If again you come back and you pick another epsilon that is smaller than that, I will still also be able to find another neighborhood that this situation will still be true. No matter how small you choose your epsilon pre-assigned, I will always be able to find a delta where this thing will be satisfied. And using a specific example, we clear this one completely, and I have a specific example for you. If that is the case, the function it will be said to be continuous if at x naught we get there and the value evaluated coincides with the limit. Now, there are functions that have limits, but they are not continuous because you do not guarantee that there will be, you can evaluate the thing. For instance, there are some functions that cannot be evaluated. For instance, sine x over x cannot be evaluated at x is equal to 0. It cannot be evaluated because it will give you 0 over 0, and you cannot find a value. There's no numerical value that coincides with 0 over 0. It's not 0 and it's not infinity. It's actually not a number. There are other cases where if you look at the step function, when you are coming from one side, you have a value. When you are coming from another side, you have another value. So that again it can be evaluated, but it's not consistent. It's not unique. So there are pathological cases that we want to exclude from our definition. So in less fanciful words, when we say this from your old knowledge, we are simply saying we can find a neighborhood where the absolute value of the difference between f of x and w naught can be made as small as we choose a priori. As small as we choose a priori because the epsilon was pre-assigned. We can pre-assign epsilon. If we pre-assign epsilon, we can always find a neighborhood where the difference between the two of them can be smaller than that. If that is the case, we say there's a limit. And if the thing evaluates at that point and it evaluates to the limit, then we say the thing is continuous. That is the thing you need to understand. If you understand that, we can build on that. But because I am not sure you understand that, I have decided to actually beat an example to death. I'm bringing you an example. We are going to kill that example by looking at it in several ways. And at the end, I'm hoping that it would have made it clear what we are saying here. Because we are just still defined here, and we are using jargons, we are using fanciful words. We are talking of for a pre-assigned real number, and there is a delta neighborhood, there is a function is continuous. But I'm not going to limit myself to that. I'm going to take an example And I'm going, both of us, all of us, we beat that example to death together. By the time we finish beating that example to death, I am hoping that by that time, all that is being said here would have been known, not just for cramming, but because you understand exactly what it is saying. I am doing that because it is that understanding that helps us to expand and extend knowledge. Okay, this is the example I'm going to give. What do we mean if we say that the limit as x tends to 1 of sine x minus 1 over x minus 1 is equal to the limit as x tends to 0 of sine x over x, and that limit is equal to 1? What exactly do we mean? First of all, before we go on, let me first of all check if that first equality is clear to everybody in the class. Do you know that the limit as x tends to 1 and it's the same thing on the left hand side, the same thing as the limit as x tends to 0 of this one in the middle? Is that clear to everybody, or to prove that? So I'm first of all staying at this first equality. Please, if it is clear to everybody except you, say so. I will explain to you. So I don't care what every other person says. Tell me whether this first equality is clear to you. If it is not clear to you, say so, because I will explain. And I will explain until you understand. Even if it means not doing anything else today until you understand. Okay, so Theophilus says it's not clear. Okay, that is one. That Theophilus says it's not clear. Okay, only one person says it's not clear. Okay, now because it's not clear to Theophilus, we will pause. Babalola also says it's not clear. So let us pause. Okay, take your pen in hand and let h be equal to x minus 1. Allow h to be equal to x minus 1. So sine x minus 1 is written as sine h. Do you agree with that? Babalola and Ario, please answer me now. Sorry, Babalola, do you agree with that? If we say, and who else am I trying to? Theophilus, do you agree that if we say h is equal to x minus 1, then sine x minus 1 becomes sine h? Is that clear, Theophilus? Okay. So do you agree, therefore, that sine x minus 1 over x minus 1 becomes the same thing as sine h over h? That's the second question. Do you agree with that? Sine x minus 1 over x minus 1 becomes the same thing as sine h over h. Okay. Now, if h is equal to x minus 1, what happens to h when x tends to 1? Do you agree with me that when x tends to 1, h tends to 0? If h is equal to x minus 1, that is, when x tends to 1, is that clear? If x minus 1 is equal to h, then when x tends to 1, h tends to 0. Is that clear? Okay. Now, if that is the case, is it now clear to Babalola and Theophilus that these two limits are the same? It's now clear, because all we just need to do is to now write x instead of h, and this middle term becomes clear. So everybody is happy now with this middle term, with this middle equation. So now, okay, so if there's no objection to that, I now go to this second equation, that this limit is equal to 1. I want to show that this limit is equal to 1. Now, to show that the limit is equal to 1, let me tell you, there is no mathematics in limit, really, seriously speaking. Limit is just ordinary spreadsheet work. So what do I mean by that? If I take this table here, I write some values of X. I'm deliberately choosing the values of X from 0 all the way to be nearly 1. Then I omit the value of 1. Except the value of 1, because that is what taking limit means. Don't look at the point itself, just look around it. When you look around it, you'll find that as sine x minus 1, if you just use your spreadsheet or your calculator, these are the values of sine x minus 1 for these values of x. These are the values of sine x minus 1 for these values of x. X is minus 1. When x is 0.4, x minus 1 is minus 0.6. When x is 0.9, x minus 1 is minus 0.1, and so on. So this column here is showing you the values of x minus 1. Now, if you divide these two, if you divide sine x minus 1 by x minus 1, you get what is on this something. Now, it is here and here only you can understand what mathematicians mean by limit. It's not in the formulas. This is what tells you what it means. If you look on this column, you can see that sine x minus 1 over x minus 1, it is 0.84 here, it's 0.94 here, it's 0.99 here, it's 0.999 here, it's 0.99999 here, it's 0.99999 here, it's 0.999999999. So it is clearly tending to something, and it is that you don't need, everybody can see that that thing it's tending to is 1. Because if you continue going closer and closer, it will just be giving you 0.999 until the 9999 becomes so many, but it will not go beyond that. It will just continue piling the 99999. That is exactly what we mean when we say the limit is 1. That's what it means. We mean that if you keep looking around it, you will see a tendency. It will be clear. Something will happen. You will see where it's going. Now, if you do not use numbers and you use plots, this blue line is showing the number as you are getting close to the value of 1, and you can see that when you are at 1, the value is 1. That is what we mean by the limit of this is 1. So let me now further comments on that. Further comments are as follows. These are numbers and graph and explanation I've given. If you subject any time you are told about a limit to this, it is laborious, it is tedious, but it is not rigorous. I hope, do you agree with me? It is laborious because it takes a lot of labor to be calculating them one by one, tabulating them, plotting them. It is labor. It is tedious because you get tired. You can easily make mistakes because the calculations are too many. But it is not rigorous because there is at no point in the work that there is something that is beyond your understanding. So I want to ask another question now. Now I'm asking the class, this idea of the limit we have just defined, that is the limit. Do you agree that the concept is not rigorous? It can be tedious, it can be laborious, that given any problem of limit, you can always formulate this table and check whether the thing is tending to a particular. It's not rigorous. It's not rigorous because there is nothing about it that is difficult for you to understand. And if you are ready to do this work, you will always know. For instance, let me tell you what we know. If you are ready to do this work for any limit, you will know whether a limit exists or not. If, for instance, if the thing is not going in any direction, you can say, well, sir, there is no limit here. I can't see any limit here. You can come and tell me that. And if there is a limit, you will see it. It will be clear. If you arrange it like this, you will see whether a limit exists. By the time you plot it, you look at the numbers and you just approach the thing, you will see it. Since secondary school, there is nothing else your teachers were telling you apart from this. But because we are lazy, We do not want to do the work of the labor and the tedium. We are looking for formulas so that we do not need to do this. I don't blame you. We are all like that. Even me that I'm teaching you now, I am like that. But I know that the fact that we don't do this work often makes the thing appear to be more rigorous than it is. It is not rigorous. It only looks so because we are looking for formulas. That's why it's looking rigorous. It's not rigorous. There's nothing to it than this. And this applies to every varieties of polynomial, of transcendental function, anything. You can always sit down, use a spreadsheet, calculate the numbers, and check. If the thing is tending to a limit, you will see it. If it is not tending to a limit, you will see it. Okay, let me now draw some conclusions. Let me type the conclusion before I go on. So some things have limits, some other things don't have limits. I'm sure you can agree with that. Let me draw another conclusion. So I want you to pay attention to this second conclusion. I want to know whether you understand what I've just said now. If there is a limit, then if you select a number, how small, there's a range that the expression will get within the number you have selected. Do you understand this sentence? And please, if there's anybody in the class that does not understand this sentence, so I'm going to explain it. I will explain it. If just one person does not understand this one, just one person is enough. If there's a limit, okay, so Ogochukwu doesn't understand. Okay, since Ogochukwu doesn't understand, don't worry if you don't understand. I'm going to explain it now. Okay, let us look at this example on the board. And I will use this example to now explain what the definition is saying. And it is that thing that you neglected, that you didn't really understand, but you crammed the formula. That's what's causing your problem. And but I have gotten a very good example now to use. Okay, suppose somebody in the class chooses 0.1. Then 0.1 is now our epsilon. I will tell you that if it is 0.1, as long as I'm within 0.4 to 1.4, I'm within that limit and the expression, because you can see that 0.94 now is less than 0.1 away from 1. Can you see? It's less than 0.1 away from 1. As long as I go close to 1, closer than 0.4 is to 1, I will be close. I will be as close within 0.1 of it, because 0.94 is less than 0.1 to 1, isn't it? Now, suppose another person comes and said 0.1 is too big. I want to take 0.01. I said, no problem. As long as I'm within 0.9 of 1, the difference will be at least within 0.01. Can you see? Can you see that the difference here, that epsilon here now is 0.01? You see, when we are at 0.4, the epsilon is 0.05. If you choose 0.01, it is even smaller. If you choose 0.001, I can get, as long as I'm at 0.93. If you choose 0.0001, as long as I'm around 0.99, I will get close. If you choose 0.000001, I will get a number that from that point on, I will get near it. Now, the question is, suppose somebody now is crazy enough, and he now chooses 0.000000 20 times 1. The answer still is, as long as that limit exists, there will be a value, there will be a delta neighborhood that I will be close enough that the answers I will get will still be within that limit. That is what that sentence is saying. That for any pre-assigned epsilon, positive number, no matter how small, we can always find a real number delta 0, that as long as we are within that delta neighborhood, we will be able to make the difference between the function and the limit smaller than what you have chosen. So we don't need to, whatever you choose, we will get as close to it as possible just by simply getting within the neighborhood. So all I'm just going to be doing, I will just be making delta smaller and smaller. If you choose a small number, I will get close to x naught by delta, a smaller delta, and I will meet your condition. If you choose 0.1, I will meet your condition. If you choose 0.01, I will meet your condition. If you choose 0.001, I will meet your condition. If you choose 0.00001, I will meet your condition. All that I will need to do is to be making delta smaller and smaller. And as long, no matter what you choose, I will meet your condition. If that limit exists. If the limit exists, I will always be able to meet your condition. If I cannot meet your condition, it means that the limit doesn't exist. That is the meaning of this. And these numbers we have chosen here shows that if we continue getting closer and closer to it without so the limit doesn't tell you what happens when you get to the point. It happens when you are as close as you like. You can be as close as anything without necessarily getting to the point. So at this point, I want to see whether we now have an understanding of this statement that we have been carrying since secondary school. They've been telling this to us since secondary school. I want to know whether we now understand this, because if we understand this, we can build on it. It is not the formula, oh, okay, what is the differentiation of x squared is 2x. There's nothing there. Where the meat is in this definition. And you cannot expand the formula you have cracked, but you can expand this definition. So if you understand this now, I will move to the next step, and I'm going to now challenge you with some other things. So I want to move on now. So I think I've used this example, beating this example today to make you to see what we are talking about. So let me go to the next step. Now, let me go to your familiar graphs. Your familiar graphs are scalar valued functions of scalar arguments. And let me give you examples. I'm sure you agree with me that y is equal to x squared. The argument is x, which is scalar valued, and the function itself is, the domain is, the range is x squared, which is, the domain is x, and the range is x squared. So you can see that the input is x, is a real number, and the output is x squared, is also a real number. If you say x is minus 3, x squared will be 9. 3 is minus 3 is a real number, 9 is a real number. So there's no problem. If you say x is 20, x squared will be 400. 20 is a real number, and 400 is a real number. So we mean that this particular case is an example of a scalar valued function of a scalar argument. Similarly, this one is a scalar valued function of a scalar argument. The scalar argument is x, and the function is sine of x. Similarly, this one is also a scalar valued function of a scalar argument. We omit the case of x is equal to 0, because if you make x is equal to 0, this thing does not have, we omit that because this thing has no value, doesn't have any definition for x is equal to 0. So that is there. Now my question, do you know the derivatives of these three? I'm asking the class, can you differentiate these three things? I want to know, let me just ask. Can you differentiate these three? Okay, everybody is saying they can differentiate, okay. What if, the second question, what if memorizations are not allowed? Can you still find the derivatives? If I do not allow memorization or any formula, I say, find for me these derivatives from the definition of derivative. Can you find them? Can you find the derivative of this? No formula. Can you find these derivatives if I don't allow you to use any formula and I don't allow you to? Okay, Ugochukwu said you can't do it without formula. Okay. 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 So somebody has said, Ajibola says with first principles. Yes, that's what I'm saying. Can you find it with first principles? Okay. So I'm not going to do everything. I'll do the first two. I'll just do the first two. And time doesn't allow me to be doing everything, but I will just. So if somebody says, get me the derivative of this, I don't want you to use formula and I don't want you to use memorization, then you have to go to first principles. What does it mean to use first principles? It means to go back to the definition and obtain the result just from the definition without cramming and without using any trick. If that is the case, then you can find it. If you are depending on formula, then you still don't understand it deeply enough. So we will look at that. So if you want to use fundamental principle, it turns out that memorizations can help you pass your exams, and you have been memorizing very well. Only general principles, advanced knowledge. You have memorized long to get this far, but it does not last forever. You get to a point where your memorization will fail. But first principles never fail. Never. They will always be applicable. Okay. Before I come back to those three things, I want to tell you that there are some functions that are functions of scalar arguments, but they have vector values. You see, before, in these ones, we have functions of scalar arguments that have scalar values. But I want to show you, it is possible to have functions of scalar values, of scalar arguments that have vector values. This is an example. If you are told that the velocity of a particle is 2ti plus sine tj plus 1 minus 1 over tk, if somebody gives you any value of t, apart from 0, obviously, if somebody gives you any value of t, you'll be able to find the velocity, won't you? Can you find the velocity given a value of t? If I give you t, will you be able to find the velocity? Okay, so if you get the velocity, the question is, that velocity you will calculate, is it a scalar quantity or a vector quantity? So if I give you t to be 5, for instance, which is a scalar, what value of velocity, the velocity you get, is it a scalar or a vector? It's always a vector. So you can see that this is a function of t. This is a function of t. T itself is a scalar, but the function itself is a vector result. You see, so we are saying it is possible for you to supply a scalar to a function, and the function gives you a vector back. This is an example. Not only so, let me ask you another question. This quantity, this function, can you be asked to differentiate it? Even though it's a function of a scalar argument that produces vectors, but can you be told to differentiate it? And if you are told to differentiate it, what sense does derivative make? You can see that we can be given a vector, we can be given a vector function of a scalar argument. Can we be told to differentiate it with respect to the scalar argument? Can you differentiate it? Okay, Oluwatobi say yes, we can be told to differentiate it, and if we differentiate it, it will give us what? It will give us acceleration. Okay. So what I have established there, is that it is not all functions that are scalar values. There are functions that have vector values. One of them is the velocity function. And you can be told to differentiate it with respect to that scalar value, and the answer you get also still makes sense, and that will be acceleration. So even though we have been working with scalar functions of scalar arguments, there can be vector functions of scalar argument, and we may be asked to differentiate them. And if we are told to differentiate them, the answer may make sense. And we have seen an institution where the answer makes sense. Now, somebody has jumped the gun and has told me, has said something here. Boluwatife said we can differentiate each component. Okay, so one trick you can use if you are having difficulty with this thing is that you take it as if you are given 3 scalar functions, as if 2t and sine t and 1 over root t are 3 different scalar functions. And if you can differentiate them one by one and you put them together again, you have your answer. That is valid. That is valid, provided the argument is a scalar and you are differentiating, because if the argument is a scalar, each of the 3 components are themselves scalars. So you are back again to scalar, you are back again to your normal comfortable zone where you are given a scalar function of a scalar argument and you are differentiating it. So you are, anytime you get a difficult problem, you take it home to where you are comfortable. You take, instead of having one simple vector question, you have 3 scalar questions, and you can solve each one of them, and there is no problem. Fantastic. So you can do this. Now, I'm now going to propose one that you cannot solve. I'm going to propose one that you cannot solve, and you will see that it is that type of problem that makes us to need. There is nothing you have learned. There will be no escape. There is nowhere you can carry it to. You will not have a solution. So I will propose that to you, and then it will now make you understand why we need new knowledge. And you will see that our seeking new knowledge is not just because we want to do difficult mathematics. The difficult mathematics is necessitated by reality that cannot be taken care of. So let me move to that now. Scalar valued functions of vector and tensor arguments. We have been looking at scalar value functions of scalar arguments. Now, I'm talking about scalar valued functions of vector and tensor arguments. Are there examples? Oh, yes, there are examples. Number one, the magnitude of V, the magnitude of a vector, is a scalar valued function of a vector because the input to this function is the vector. Its value is a scalar, but the input, the argument, is a vector. So you supply a vector, and this function generates a scalar, which is called its magnitude. Now, suppose I tell you now to differentiate this with respect to V. There is no mathematics you know. All your mathematics breaks down, and all the mathematics you know in this world breaks down at that point. You can't do nothing here. No escape here. Let me make it worse. I1t, which is the trace of a tensor, is the first principal invariant. I2t, which is the trace of its cofactor, is the second principal invariant. I3t, which is the determinant of the tensor, is the third principal invariant. They are all scalar valued functions. They are all scalar values. I1 is a scalar, I2 is a scalar, I3 is a scalar. But they are functions of tensor, because for you to find I1, you must know the tensor, and you get I1 from the tensor itself. So the input here is a tensor, but the output is a scalar. Question: can we differentiate these with respect to their arguments? Can we differentiate I1 with respect to t? Can we differentiate I2 with respect to t? Can we differentiate I3 with respect to t? Can we differentiate the magnitude of a vector with respect to the vector itself? With the knowledge we have so far, we need new knowledge. You cannot get the V of the magnitude of V. You cannot get the T of the determinant of the tensor, and so on. You can't get them. All the difficult, what you think your math that you know so far is difficult, it is still very weak. It cannot go this far. This is the bus stop for all your mathematics. And all I am trying to do, I am just trying to expand your mathematics a little to be able to handle this kind of situation, which all your calculus that you know in your life cannot even touch. They are beyond it. They lie outside it. But there is calculus that gets this far. And for me to introduce that to you, you have to get out of your cram mode. You have to go back to first principles. If you understand the one you know now in first principles, it is very easy to expand it to what you want to know now that is beyond it.